Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Code Hunt makes programming fun. PEX for fun. So we have this word fun twice, and I applaud because fun is the way to go in life, and this is what I want, and this is what I don't want to give to my students, and so fun is the word. But then the other one, I completely disagree with the Code Hunt makes programming fun. Because programming is indeed fun. I don't know for you, but for me, it can be completely thrilling. I just stay on my computer for hours with this magic, with this mindset, this pure programming mindset where you have deeply concentrated and you have indeed a whole lot of fun. So why? On the one hand, we say Code Hunt makes programming fun, and on the other hand, we know that intrinsically programming is fun. So in programming, there is one kind of fun, one special kind of fun, which is bug fixing. There is something going wrong. Your program does something unexpectedly. So you expect something, and the output is another thing. And now you start to make some hypotheses. You start to add some logging statements to understand exactly what happens, and it can take hours to find the first to have an explanation, and then to have a fix, and then to find a fix for this bug. And so bug fixing is fun indeed. And for a couple of years, I've started the meta bug fixing activity, which is automatic repair. So designing programs that fix bugs directly. And so this is what I will be talking about today. With this, so programming is fun, bug fixing is fun, and meta bug fixing, which is automatic repair, is even more fun. So I come from France, from Lille. Where is Lille? So this is all Europe, France, UK, Belgium, Germany here. And so Lille is in the northern part of France, just here. Very close to Belgium, so we used to drink Belgian beer a lot. And yesterday Judith asked me about the specialties of Lille. We have a very good carbonade. And at the very end, on the last slide, I will tell you about the best dessert that you can have in Lille. But this is only for the last slide. And so, yeah, I'm an associate professor there at the University of Lille, which is one of there is one of the biggest computer science departments in France, and a researcher at INRIA, which is a research institute for computer science. So it's co-located with the university, so I spend most of my time at INRIA. I worked in Germany for 3 years before coming to Lille, and so my main research interest is automatic software repair with three kinds of things. So automatic patch generation, so like automating the bug fixing process as we practice it as developer, but also what I call a runtime state repair. So it's repair at runtime where there is, instead of having a crash, you try to change the application, the program state, so that the program doesn't crash or the request doesn't crash or something else. So it's slightly different. It's still repair, but it's a different kind of repair. And I like to, it's not I think that we can we will be able to automatically repair bugs only if we really understand the deep nature of bugs and the deep nature of bug fixing, which is slightly different. So I'm doing a lot of empirical studies on what bugs are, how you fix them. And so I have those three activities. And so on the technical side, so I do most of my experiments on Java because of this missing link here. So we have, in my group, we have a very strong expertise in Java source code analysis and transformation. So we have the perfect tools to manipulate ASTs, to manipulate test cases, and so what's needed for automatic repair. Okay, so what's the Reaper game? The typical Reaper game. So we are not in Code Hunt. So we've already seen yesterday that in Code Hunt we have two different games. The first one is the classical one. We have a specification and we try to code the specification. And the second one is we have nothing and we try to reverse engineer the program. The typical Reaper game is slightly different. You have a program and you have a test case. Like this one, it's a real test case. And the test case is failing. So a user reported a bug. Maybe the same user or a developer wrote a test case to highlight the bug. So this test case is failing. And the goal is to make it passing. And so this often happens that you first write the test case. So you first write the test case and then you say, okay, I want to make it passing. So I have the user. He told me that there is an error when you have 0 entries in a simplex solver. So this is a real bug from a real library, math library from Apache. And the test case is as this one, and we can see what's the test case. We have a typical code, and at the end we have the assertion. So the assertion is what highlights the bug. So the assertion is failing here, the red one. And now we are in real life, so the developer who wrote this code left, so I'm the developer who has to fix this bug, and I have to understand. So, okay, 0 entries in simplex solver. So probably the bug has something to do with 0 values. Yes, but there is one here, one here, one here, one here, one. Okay, there are many zeros. It's really hard to know which one is the problematic one. Okay, so the bug is in the output of the simplex solver. So maybe the fix is in the simplex solver class, but well, maybe not, because maybe the bug is actually induced by something in the constraint class, or in the linear constraint class, or maybe in the linear objective function. So I don't really know. So the game here, the game consists of understanding what happens, because simplex solver, it's not necessarily natural for all of us. Then where it happens and what to do. The final solution is actually for this real bug. The real patch is this one. So we have one character change in a method. But as we saw yesterday with Willem, a single character change can have a huge semantic impact. And even if the final solution, so this is where we want to go, what's the path to get there? The path to get there in this case, and this is a main difference with Code Hunt, what we've seen so far, is that we are dealing with large things. So in this example, at this point in time, when this bug was reported, it was more than 38K lines of code, more than 200 classes. And the specification, so the test cases, is even larger than the application, so 40K of specification, and more than 180K test cases. So this sets up somehow the size of the search space. So I have to understand where is the bug here, and what I should change. So, what is Reaper? More formally, according to the Reaper game we've just seen, we have a specification S, a program P, and so the very standard question in programming, in computer science, is the correctness question. Does P comply with S? Correctness, usually binary, even if it's not always the case. We can have the synthesis problem. Okay, we only have a S, and find the program P that complies with S. And the repair problem, which is rather new in the literature, for some reasons, I'm still looking for those reasons, is slightly different. It's between the two, it's like this. It's, okay, you have a program P and specification S, but P doesn't comply with S, and you are looking for a change C such that the change applied to P complies with S. So we have something like this. So definitely it involves this notion of specification and satisfaction, and also this notion of change, so edits on the existing program. So this is a repair game that could be played. So if we want to have repair games in Code Hunt, we give the players P, S, and we ask them for a change to fix the bug. But so this is a basic repair problem, the basic repair game, which is fun in itself. But we can have much more repair fun on the specification side, because in real life, so first the specification may be incomplete. Usually we have test suites. It's only some input points, some data points, and so having a partial input domain, a partial error domain makes the repair problem statement even harder. The specification can also be implicit. So this kind of specifications of program shall not crash. It's not necessarily written anywhere. And so sometimes we try to repair an implicit oracle in this way, in this case, which makes things more difficult. And the specification may itself be incorrect. So when we use test suites as specification, what we often see in real test suites is that sometimes there are some commits which make test cases passing, but some commits slightly change both the test case and the program, which means that the test case before was incorrect. So you cannot really take the specification as a untouchable truth that you cannot touch. So this is the other kind of repair thing. So at the end, as we said with this P plus C, today I see repair as a local synthesis problem, where we have, let's say, 99% of the synthesis that is already done. This is the existing program, and you try to synthesize the remaining percent of the program, and this is a fix. This is a fix you are looking for. And so let's assume that you can perfectly identify where is the problem. Then the local synthesis consists of synthesizing the part where the problem is. So for instance, if you can identify exactly which if statement is buggy, you can remove the existing code and you try to synthesize only the if statement to repair the program. So we have, in this case, local synthesis where we have the complete program. We have 99% of the solution. We have some kind of fault localization technique that tells us that this if is faulty, and then we synthesize it. And so yesterday, Daniel, in this hint system, told us something like change this line to capture the code. It's exactly identical to what we have here. Change this line to repair the code. So if we can find the exact location, we have a synthesis problem. And so we have explored this direction in a system called Nopol, that I will present now. So we are focusing on repairing buggy if conditions. So in general, like 10% of commits of bug fix commits are one-liner fixes, and among those 10% of one-liners, 1/3 are changes in if conditions. So it's a common kind of bugs. So we want to repair those kinds of bugs. So assume that you have such a piece of code, test cases which is failing, and we want to find the exact place where the bug is. What we do in Nopol is what we call, so we reuse the term from an ICSE 10 paper by Emina Torlak and colleagues, which is a concept of angelic value. Let's assume that an angel can come during execution, change slightly the program state, and the execution continues afterwards. So we have failing test case and passing test case, failed test case. So the failing test case starts, executes, and so on, and arrives here. Before executing the condition, an angel comes down to Earth and says, this if condition should evaluate to true. This is true. And you resume the program execution. You come to the assertion at the end, and you see whether it fails or passes. Oh, it fails. You start again. You come again to this if condition. The same angel comes, but this time set the condition value to false. And by setting it to false, the test case passes. So what we have here is that we observe an angelic value. We find an angelic value, which is a value that is arbitrarily set at runtime to enable a failing test case to pass. So if you have a failing test case executing, I don't know, 100 and 100 if conditions, you can go through each of them one after the other, asking the angel to manipulate the execution and see whether you have and see whether the test case passes afterwards. If you have an angelic value, you've done 50% of the repair process. You know that at this point of the execution, if the new code produces the angelic value, the test case passes.
Yes, actually, if I have 100 if conditions, wouldn't I have 2 to the power 100 different possibilities to try out, to find the angelic values for each one of them?
No, for two different reasons. First, because we assume a single point of repair. So we are at least try them one by one. And second, because we assume, but it's very close to reality, that during a test case execution, an if condition is always evaluated to the same value. So a single test case, usually for a given if, it's always true or false to some extent, but we have empirical data backing up this claim. So we have this, what we call angelic fixed localization, where we have this where, and so we find where we can synthesize the code to fix the bug. So for some properties, the search space is 2 times n, where n is the number of if conditions. We have an interesting property, which is if we cannot find an angelic value, it means that the bug cannot be repaired by changing an if condition. It's another kind of fix. And so if you can find an angelic value for a given if, for all failing test cases, you have an input-output-based specification of the repair problem, where you are looking for a Boolean expression here because we are in an if condition. So we are looking for a Boolean expression such that for each test, for each failing test, the Boolean expression of the execution context returns the angelic value. And for each passing test, you don't want to break the existing functionality. So for each passing test, you want the synthesized expression to return the actual executed value. So you may change the expression, the synthesized, the new if that you are looking for may be different from the previous one, but for the passing tests, it should give the same execution, the same value after evaluation. And so now we have an input-output-based specification of the repair problem. We know that we may be able to find a piece of code that returns the good if conditions. So here we have the context. So the context of a if. What is the context of a if? So in Nopol, we collect a number of variables in the program under repair. So of course, all primitive variables. We aim at, so as I told you, I work with Java, so we aim at repairing Java programs. So we collect also the nullness of all of the variables, whether an object is null or not, because to be able to synthesize if A is not null. We collect the values of side effect-free methods with no parameters. like list.size, for instance. Of course, all constants. And we have a piece of secret sauce here, which is one of the famous repair technique is called GenProg. So by Weimer, Forrest, Claire-Leguès, and colleagues, 2009. And the key assumption in GenProg is that the repair comes from elsewhere in the code. Last year, we've done an empirical study published at ICSE where we verified this assumption based on repository mining. We looked for commits. That are only composed of code existing somewhere else in the code base. And depending on the way you count, between 10 and 50% of commits indeed never invent new code. They only rearrange things. So here we can do the same thing, and this also has some empirical validity. A lot of if condition repair, they just rearrange the if conditions, or they just reuse a compound condition from elsewhere. So what we can do is that we can collect, we can evaluate complex expressions. So by complex I mean a method called with parameters. We can evaluate them before synthesis because we cannot encode the semantics of those complex methods during the synthesis process. So we collect all this, and we have a bunch of values. And now we have really an input-output based specification. When the context is input, the output is the angelic value that I've presented before.
Yeah. Maybe you said it and I missed it. So you said that you looked at the actual repairs and actual fixes, and how many of those were only if conditions? I mean, do you have what's the evidence that there's a lot of bugs that are just
so between 10% of bug fixes are one-liners, and and approximately 1/3 of one-liners are if condition fixes.
Okay, so like 3% of the fixes are okay.
Okay, so now in Nopol we start the pure synthesis part, and we use a component-based synthesis. Wonderful technique published at ICSE 10 by a team from Berkeley, which encodes the code synthesis as an SMT problem. I won't go into the details, but basically what we have, the input-output based specification. So we have the input, which is here. So here we assume that the input is only two variables, one variable index and a constant 0. We put components in the synthesis. So what can we have in the synthesized expression? So for instance, here we can have only one negation operator and one inequality operator, but we can have as many as we want. And we have the output. And the synthesis assigns one line number, so it denotes a line number to each of those inputs and outputs. And the solver, the SMT solver, is asked to find some wiring between those components. So here the solver searches for 4 integer values. And how those integer values are interpreted? So let's assume that the solver finds those values. I really miss the bottom of the slide, but anyway, no, I have to get them, sorry. Yeah, let's give it this way for now. So the condition is connected, so the synthesized code is connected to the component, the line 3 here. So line 3 is the negation operator. The negation operator is connected to the output of line 4. So the output of line 4 is the inequality operator here. And the inequality operator is wired to line 2 and line 1, which corresponds to the two input variables. So at the end, the synthesized expression. So the SMT solver gives us only those 4 integer values, and they correspond to this synthesized expression. And we can use exactly the same thing to extend this to object-oriented fixes. Like here, we encode also as input the expressions we want to have in the repaired expressions. So for instance, list.size, list is not null, and so on. We also ask for values to the solver, and at the end, here we almost see it. We have the output which is connected to line 5. So line 5 is the end expression connected to 3 and 4 and so on. And so we are able to synthesize this object-oriented code. So this fix. So list is not null, and list.size is lower than index. And of course, we can have many components, and some components may not be used, and in this case, they just give the answer to all questions in life. So what is Nopol? So we have this angelic fixed localization, which gives us the answer to where the bug is, where the code should be fixed. We have the runtime value collection, where we collect a large number of things. We encode this into SMT. As a synthesis technique, we could use another one, and it gives us, based on the where, what should be, what is the new code, and then we have the patch synthesis. And so this is what Nopol is. Standard evaluation, we take real bugs. So on 2 or 3 libraries here. So Apache Common Mats, Apache Common Slang, which is up to 64 lines of code. We run the system and we observe different kind of things. So this is the kind of patches that are synthesized by Nopol. We see standard if conditions, and as a result of this evaluation is that okay, so Nopol fixes conditional bugs of large object-oriented Java source code. The repair takes less than 2 minutes. The patches often differ from the original one, which is always surprising, but it's related to the next point, which is there often exist multiple different patches. So it seems that humans select one patches among a set of different patches, and all of them being valid, let's say. And as soon as you play with the automatic, so this is one component of the fun part of automatic repair, is that you observe that software is much more plastic, let's say, that you might imagine in the first place. Yeah.
So your repair means that the test cases pass, right?
Yes.
And how many test cases actually go through the patch? Because my kind of issue with this kind of repairs is always that making the test cases pass doesn't mean that you fix the code, right?
You're right.
So when you say that the patches are different, you manually check that they're semantically equivalent?
Yeah, we have this.
And
the numbers
they are all?
For some of them, they are semantically equivalent. For some of them, they are not semantically equivalent, but they seem correct also, according to our understanding of the domain, because we are not the domain expert. And for some of them, this is a discussion slide after, the test suite is not enough. But it's not
they're not semantically equivalent, but you think they're correct? It's tough to say, right?
It's tough to say.
Any reasonable program, right? So for how many of them they're semantically equivalent?
Semantically equivalent or semantically correct?
No, semantically equivalent. Because semantically correct, you don't have a specification, right? So you cannot really
exactly. I will tell you after, because in the paper table I have another column which is the original patch. But here I only have this one. I think it's 1/3.
1/3. Okay. And do you remember, for how many test cases we're going through the?
So it's between 4 and CSA 60 or 70. in this.
So we're going through the condition that you fix.
Yes,
Okay.
yes, exactly. But the number of test cases is always, I don't really like this metric because you can have one test case which is very large with many, many assertions. So it's actually a very, very strong test case for the condition. So
yeah, but that's already good because I mean, some of the work I've seen, and you had like 1, 2 test cases going through, which means that you can fix it very easily, right? You just have to patch it so that test case, behaves as expected. Sometimes you don't even have an assertion, so as long as it's fresh, it's fixed, and so anyways.
Exactly.
Okay, well, thanks.
I agree. So some discussion. So what's the limitations of the system? So first, the synthesis limitation. We are not able to, since we encode somehow the semantics of the repair in SMT, we are not able to synthesize code containing methods with parameters. Large test cases are always a problem because in large test cases, the key assumption that you only evaluate the if to true or false per test case doesn't hold anymore, and so this is an issue for us. Weak test cases, of course, when there are no assertions or bad assertions or too weak assertions, it's bad. The angelic value, the angelic fix localization technique works very well unless you have the if something break in loops, because if you put an if something, so when the angel comes, the angel is an angel, he's never guilty, he's just beautiful and perfect. So the angel puts true, if true, or if true is okay, but if false is an issue in loops because you get into an infinite loop and so on. So perspective of such system using other synthesis technique to overcome the first limitation, and so we are exploring the automatic repair of infinite loops with such kind of ideas. The automatic repair of preconditions, method preconditions, the classical. So if you are in a poor language with respect to preconditions such as Java, you have the preconditions are written as if something throw a new exception, and so we can repair them also. We're exploring this. So so this is one part of the what I've claimed in a previous paper is that in repair we have to be very careful about what we are talking about, exactly as when we compare two code hunt problems, whether it's capture the code, so it's a reverse engineering problem or it's a specification problem, it's not the same. So it's not the same thing to repair buggy conditions, unhandled exceptions, memory leaks, and so on, and then we have to be very careful. We have to qualify the problem and the evaluation data set. And we come to the last line. No, not the last one, because the last one is about the dessert from Lille, which is really good if you like chocolate. But no, just before this, repair and code hunt. So yesterday and today, I've seen many relations between between repair and what we've seen on code hunt. So first, of course, the hint generation system presented by Daniel yesterday. We could use exactly the same kind of technique as angelic value to speed up finding the hints. We could also use component-based synthesis instead of dynamic synthesis. It may fasten the hint generation system. I would be very interested in observing the player's repairs. It's similar to what we've done with commits. The very last step in the code hunt game, is it adding an assignment, changing an existing assignment, changing a return value, and so on? So we could really understand the nature of getting to the solution, and to understand the path from the problem to the solution. But the third thing is this notion of repair duels. So as I claimed at the beginning, bug fixing is very fun and very addictive. So maybe a repair duel where the goal is you have an almost correct implementation and you try to make it correct. This might be also very fun and very addictive for players. Or this might be just a break in the game experience. So sometimes you have a specification problem, sometimes you have a reverse engineering problem, and sometimes you have a repair duel where you have to find so it can be a break in the game experience. And so if we go for repair duels, there is this key question, which is what makes a good repair duel? It's a hard question. Yesterday, I've started to play with the system, and basically there are some small changes that make all test cases given by PEX failing. Some of them result only in one failing test case. So I tend to think that a good repair duel has a good balance between passing and failing test cases. Otherwise, it's kind of depressing that you have only failing test case. You don't want to repair this. It's not motivating. So there is something in the game experience between the failing and passing. There is definitely something with respect to what Willem told us about yesterday about the model counting. Maybe also it's more fun to repair, in a repair duel, to repair a program which is correct to 90% of the input space, up to 90% of the input space. I don't know, but something has to be explored here. And the missing point here is if we are able to qualify those 2 points, we may be able to generate the repair duels from the existing solutions. So modify the secret code so that we have a buggy program, but which is fun with respect to the balance between failing and passing and the model counting. And so if we can generate the repair duels, it's good with respect to having a lot of data because, as far as I understood, one issue in Quadrant is the number of problems we have. So if we can generate new fun problems with a good game experience, that would be a cool thing. So conclusion, automatic software repair is fun. So this is the takeaway of my talk. Because of what? Because we have the fun of the search space, which is huge. We have the fun of dealing with the specification, which can be incomplete, which can be incorrect. So it's always very, very fun to understand the nature of specifications, and the synthesis, the program synthesis is really fun as well. And when you have a system, so a demo of automatic repair is always very boring because it's just a console output of the system. But at the end of the output, where you can read patch found, it's always a very good experience. So this is the end of my talk, and this is a wonderful picture of Merveilleux. So Merveilleux, what do we have in Merveilleux? So we also have a distribution, different components, like in automatic repair is a specification search space. So in Merveilleux, we have basically 3 components. So the Merveilleux, when you first look at it, it looks like fat because there's a lot of chocolate, a lot of cream, and so on. But as usual with French cuisine, it's actually very, very fine. So in the middle there is a meringue. So meringue is something with eggs, but it's very, very, very light, so that it just as soon as it's in the mouth, it disappears. So we have the meringue, then we have some cream afterwards, which is excellent, and at the top it's just dark chocolate. But what's incredible with Merveilleux is that even if it looks very fat, it's very fine and very light at the end. So this is a specialty of Lille, and so since Lille is only 45 minutes away from Charles de Gaulle, 1 hour away from London, 1 hour away from Brussels, you are all welcome to visit us in Lille and to try les Merveilleux. Thank you very much. This is the end of my talk.
Could you go back to the slides, previous slides? I like the kind of a proposed work on like automatically generating good duels. But I don't know whether you already mentioned that, like, for what you propose, a repair duels, the coding duels naturally support that, right? Basically, instead of giving you return 0 as a starting point, you just give them the faulty versions.
Yeah,
I
exactly.
mean, with existing code hunt, you could already prepare these kind of tools
Yeah.
for training students in terms of their debugging, repairing skills, right? So, I mean, I just would like to clarify that. I think because we have seen almost all of them just start with return 0, return X, right? But the platform is very flexible to allow you to put whatever initial code to start with, whatever code comments as a hint for telling students what kind of requirements you need to satisfy, rather than pure guessing, right? So I think, but I like the last bullet point is that could we leverage the data, right, the playing histories of all these players to evolve or produce new games or new coding tools, right? Maybe initial tools would be just pure guessing, but just for the mistakes that from the mistakes being made by players in the past, we may just produce some specific, more like repair tools, like what you said. Yeah.
I completely agree. The thing also here, what struck me yesterday is that so in automatic repair, okay, automatic repair is fun, but actually there is a hidden part which is not fun at all, which is finding actual real bugs for your next ICSE paper, because ICSE wants you to repair real bugs. And so finding bugs is easy, but reproducing them is horrible. And it takes you a whole lot of time. So for a long time, I said, okay, but we can generate bugs. It's very easy. We just take mutants, and that's fine. But then there is it's not realistic anymore. So for your next ICSE paper, it's an issue. But here, it's different. We can generate them because the goal is the game experience, and maybe the skill building. So in this case, it's perfectly fine to mutate the code according to like game experience metric, and it makes perfectly sense. So it's really cool. Then, thank you again.